Remember that insertion into a hash table means we first compute some hash value, and then we mod that hash value by the length of the array in order to find the index of insertion. And remember that because we want our array to be relatively small compared to the theoretical possible realm of elements, and because we might have multiple different elements potentially having the same exact hash function, assuming we don't have perfect hashing, we could end up with a situation that we try to insert two different elements into the exact same spot. This is known as a collision. How do we deal with collisions? One simple solution is called open addressing, which is also known as linear probing. So to exemplify this, let's take this empty array. This is the backing array of a hash table. It has length 5. And let's say I want to insert these 3 elements. So first, just for convenience sake, I'm going to compute the indices to which each of these corresponds. So the hash value, so for each of these, I'm using the ASCII value as its hash value. So if I have a hash value of 65 and I have an array of length 5, the index would be the hash value modded by the length of the array, which is index 0. 70, so f would be hash value 70. 70 mod 5 equals 0. Uh-oh, that's going to be problematic. These two are going to map to the same index. And then 71 mod 5 is 1. Okay, let's see what happens. So first, I try to insert A. It should be at index 0. I look in my array. Oh, index 0 is empty. Perfect. Let me stick in A. Done. Next, I look at F. F should also map to index 0. I check my array. Uh-oh, something's already in index A, and it's not in index 0, and it's not F. So what do? Open addressing or linear probing tells me, let me just try checking the next slot over. So I would jump to index 0 because that's the index that I got. It's full, so I would just check 1 over. Oh, this slot is empty. Perfect. I'll just go ahead and insert in here. Done. Now let's say I'm trying to insert G. G has a hash value of 71, which modded by 5 gives me an index of 1. I check in my array. Uh-oh, something's already here. That's okay. Linear probing tells me, let me just go to the next slot. Oh, it's open. Perfect. Let me just insert it here. So now if I wanted to find an element, let's say I want to find A. Again, I know that it should be at index 0, so I jump to index 0. Yep, A is there. What if I was looking for F? Well, F, I would jump to index 0. Nope, that's not F. Let me check the next slot over. Oh, yep, I found it. So if I'm doing a find algorithm, I start at the position at which I should have hopefully been inserted. And if I don't find it there, I will keep iterating until eventually I hit an empty space. So what does that mean? Let's try one more example. Let's see, G8, so F, G, H, I, J, K. Yeah, let's try K. G, H, I, J, K. So I think K, if I'm not mistaken, has a hash value. It has an ASCII number of 75. So what does this mean? This means that when I mod it by the length of my array, I get 0. So what happens if I try to search for the capital letter K in this array? I get an index of 0. I go to that index. This is not equal to K. Let me check the next one. This is also not equal to K. Let me check the next one. This is also not equal to K. Let me check the next one. Oh, I hit an empty cell. If I had ever inserted K, I would have found it in one of the non-empty cells. So if I've reached an empty cell, that means K does not exist in this array, in this hash table. The reason why we call this linear probing is because we go to the initial spot and we linearly probe. We check 1 by 1 by 1 in a straight line down the array. So that's why it has the colloquial name linear probing. We're probing linearly to find our element. And the reason why we call it open addressing is because, remember, an array is defined as a contiguous block of memory, and each of these cells can be defined as a memory address. Really, it's the starting memory address of each cell that we can use to define. So open addressing is saying, even though I map to a specific index of my array, aka a specific address, I'm allowing my insertion or my find to go to other indices or other memory addresses. So I'm doing open addressing. The addressing is open. I can go to different slots of my array to find the given element. What happens when my backing array gets full in linear probing? So let's say I did want to actually insert element k. I would go to index 0, that's full. Go to index 1, that's full. Go to index 2, that's full. Go to index 3, oh, that's empty. I can insert it here. And let's say I also want to insert b, which the hash value, the ASCII value of b is 66. Therefore, the index is 66 mod 5, which is 1. So if I'm trying to insert b, I would start at index 1. Nope, that's full. Index 2, that's full. Index 3, that's full. And I would insert it into the first open slot. What would happen if I tried to insert one more element? My array is completely full. So what I would have to do is create a new array, reinsert all of my elements into this new array, which, even though their hash values are staying the same, the length of the array by which I'm modding will be different. So their indices may be completely different. They likely will be different. So if I do this, I would then, reallocate. So I would create a new array. In this case, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. Let's say I doubled the length of my array. And then for each element, I would reinsert it into this other array. And remember, in a hash table, I don't remember the order in which I inserted the elements, so I'm just going to arbitrarily do it left to right. So the first element is A. So the hash value of A is 65. Mod 10 now, because my array is twice as long. 65 mod 10 is 5. So I would insert A in index 5. Then I see F. F's hash value is 70, but now mod 10, not mod 5, I get 0. 71 mod 10 would be 1, so G goes into 1. K, 75 mod 10 would be 5. I go to position 5. Uh-oh, something's already there. Linear probing, I check 1 over, and I insert it there. Now I try B. So B is 66. Mod 10 is 6. Uh-oh, position 6 is already full. I try the next one over. It's empty. I insert it there. And then I would deallocate the other array. And now this new array is the array of my hash table. So remember when we were talking about probability of collisions, we talked about this notion of load factor. We wouldn't wait until our array is completely full before resizing it. We would wait until we reach the load factor, so the number of elements divided by the number of slots in my array. Once that reaches the load factor threshold that we've specified, we would immediately resize our array then. What about the time complexity of this? If you think about it, if I insert n elements, theoretically, I could accidentally have a bunch of elements. I could have big O of n elements in a contiguous block. If I look for a specific element, I might have to accidentally iterate over all n of my elements. This is precisely why hash table insertion, find, and remove using open addressing or linear probing is big O of n in the worst case. The reason why it's big O of 1, so constant time, in the average case is because we can design our hash table using our derivations of the probability of collision and therefore expected number of collisions to expect that on average we have 10 collisions as opposed to big O of n collisions. 10 or whatever constant we pick is a constant, so that would mean constant time in big O on average.